Question number 1, find the effective resistance. Find the effective resistance. Find the effective resistance between A and B. Find the effective resistance between A and B. In the following diagram. It's called a skeleton network. Find the effective resistance between A and B in the following diagram. It's called a skeleton network. It is there in the reader. Shida, you asked me, right? Somebody say ask me and I send the video for this. All right. It's called skeleton network. It is there in the reader, but still. Okay, right. All resistors are identical. Everyone, can you all hear me? Find the effective resistance between A and B. All resistors are identical. Altogether, there are how many resistors? 12 resistors, okay? 12 resistors. 12 resistors. Find the effective resistance between A and B. A and B are actually opposite corners of a diagonal. Opposite corners of a diagonal, okay? Find the effective resistance between A and B. It's called a skeleton problem. It's a standard value. Standard value answer is 5 by 6 times R. I'll tell you. Okay, right. Tell me when completed. Okay, right. Okay. So what is the question? We have to find the effective resistance between A and B, right? This is what one corner of the cube. This is opposite corner of the cube. Am I correct? So this is like the room itself, and there are like how many edges? 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Altogether 12 edges, right? Okay. Now, what I'll do is I'll connect a cell across the diagonals. A cell across this. I'll just connect a cell across this. Look at this. A cell across this. And the EMF of the cell, I can call it E. Okay. So I'll just connect a cell across which I need to find the effective resistance. There are 3 such questions, but only the first question is needed. Second question is find the effective resistance between ends of one side. Ends of one side. Okay. Third question is find the effective resistance between ends of face diagonal. Face diagonal. Face diagonal means this and this. All right. Front face of it, no? Diagonal. There are 3 such questions, but we are looking at the cube diagonal only. Cube diagonal. All right. We look at only one question. Cube diagonal. Find the effective resistance between the corners of this. Okay. Diagonal, opposite diagonals, opposite ends, no? And what you will do is you will connect a cell like this and you will split the current. Tell me, what is the current going into the circuit? I can call it 3 times I. I call it 3 times I. Why do I take 3 times I? I could have taken I, then the current would be I by 3, I by 3, I by 3. Because when the current enters this, the current equally splits up into 3, right? Look at that. It sees 3 different paths. See this? I'll just mark the paths now. This is I. One current is I. Second current is also I. Third current is also I. Why are the currents same? Because the circuit is symmetric. I can tell you, if it takes this path, look at this. Resistor number 1, resistor number 2, resistor number 3. You are at B, right? If you take this path, resistor number 1, resistor number 2, resistor number 3. You are at B, right? If you take this path, resistor number 1, resistor number 2, resistor number 3. You are at B, right? So whichever path you take, after the third resistor, you will reach the point B. Am I correct? Correct. That is called symmetry. So when this current enters the junction, it actually sees identical paths to travel to B. All right. See this. If it takes this path, R resistance number 1, resistance number 2, resistance number 3, resistance number 1, resistance number 2, resistance number 3, resistance number 1, number 2, number 3, number 1, number 2, number 3, whichever path you choose, current would eventually has to pass how many resistors? 3 resistors. Correct. 3 resistors, right? Look at that. Whichever path. This is 3I getting into the circuit. No, that will be equally split up. So one current will be I. Let us follow each current now. Tell me what? This current comes right here, I. Now it splits up into how many paths? 2 paths, right? That current breaks into 2 paths. Look at that. This current joins there, reaches there. It breaks into 2, no? So what must be the currents then? This current will be I by 2. This current also will be I by 2. I will be splitting into 2 equal parts, right? Why are they equal? Because resistance number 1, resistance number 2, you are at B. If you choose this path, resistance number 1, resistance number 2, you are at B. Understood? Identical paths, right? So that current will be split up into I by 2, I by 2. Let us follow the other current. This current, I reaches this junction. Tell me what? It is split up into, tell me same way, I by 2, I by 2. Am I correct? Correct. Let's look at the third current, I. Third current, I. It reaches here. This current will be how much? I by 2. This current will be how much? I by 2. Am I correct? So first, 3I current went into the junction. That actually got divided into 3 equal parts. There were 3 paths, right? 3 paths, 3 equal currents. One current is I, one current is I, one current is I. Correct. Then this current comes right here. Then there are 2 paths. One path like this, one path like this. So current will be equally divided, I by 2, I by 2. All right. 2 paths, it is I by 2. 3 paths, it is I by 3. Correct. And tell me, similar way, this current I reaching here will be split up into I by 2, I by 2. Similar way, this current reaching here will be split up into I by 2, I by 2. Now, can you tell me, look at this. This current is going up, I by 2. This current is coming here, I by 2. Together, that will be I, right? Am I correct? This current is going up, I by 2. This current is I by 2. They join together to become I, right? Am I correct? So let us look at the other I by 2. I by 2 coming here, I by 2 coming here, join together to become I, right? Similar way, I by 2 going up, I by 2 going up, they join together to become I here, right? And those 3 I's, this I comes here, this I comes here, this I comes here, together they flow out as 3I, right? Correct. This I is going up, that reaches the junction. This I is coming here. This I is also coming here. All of them together will reach the junction and it will be 3I. What actually went into the circuit? 3I. What came out of the circuit? 3I. So that completes the distribution of currents. All right. Now we just have to apply Kirchhoff's voltage rule. What is Kirchhoff's voltage rule? You know what? As you walk, put negative plus, you remember. See, I'm going to take this loop. I can have so many loops in this, but I will always go with the simplest loop. The simplest loop. Look at this. This loop, this loop, this loop, this loop. Do you understand? Right, the smallest one with least number of resistors. Let us start from A. Start from A, okay? See the path I'm taking, okay? I'll draw it somewhere here. I'll draw it here, okay? I'm going to take along, go along this path, and come back here, right? Like this. Understood? So tell me, I can write down equations as I go. First one, current into resistance, right? When current into resistance, I into R, isn't it? Negative. Why negative? Because you're walking along the current, right? Then about this, tell me, I by 2 into R. I by 2 into R. That is also negative, right? Because you're walking along the current. Again, you're going up, I into R. I into R, right? I into R. That is also negative. Am I correct? Then I come right here, cells negative. Cells negative means plus EMF should be equal to 0. How to apply Kirchhoff's voltage rule? I into R, I into R, I into R. Then plus EMF should be equal to 0. Completing the circuit, right? Okay, so what do I get now? This E will be equal to, this is IR comes to right side. Then half IR comes to right side. Then again IR comes to right side. So that makes it what? E is equal to, this is 1, 2, 2.5. 5 by 2 times IR, equation number 1. All right. And if I replace the whole cube with a single resistor like this, what am I going to write? EMF is equal to 3I into R effective, right? Correct. Voltage EMF is equal to 3I into R effective, right? Current into resistance is voltage, right? I'll replace the whole set of resistors with a single resistance called R effective. All right. What is the current that went into the cube? 3I, right? That is equation number 2. Now I can equate them. 3I into R effective is equal to 5 by 2 times IR. So if I cut I and I on both sides, R effective will be what? It's equal to, this comes here, 5 by 6 times R. Effective resistance will be equal to 5 by 6 times the resistance of one side. Got it? So it's all about splitting the currents and then writing down the equation. Okay, we'll do it one more time. All of you got this? Everyone, please. So the question is what? Find the effective resistance across the diagonal of the cube. So first thing to do is to connect a cell across the diagonal. Draw the cell like this. This is the cell, okay? All right. Okay. The EMF is E. Okay. EMF is E. All right. I just connected some random cell across the whole cube. All right. And what is the current that is going into this? I call it 3I. Or you may better call it 6I. Then you won't have to take I by 2 then. Understood? If I take 6I, this will be 2I. And that'll be better, right? Okay, fine. So let's take 6I. It's up to you. You can even take it as I. No problem. All right. There won't be fractions this way. Right. So 6I goes into the circuit, okay? 6I goes into the circuit. What will happen to it? Tell me, there is this first splitting. This will be 2I, and this will be 2I. This will be 2I. All the paths are getting identical currents, right? 2I. All right. Okay, there are 3 currents, right? 6I getting into the junction will be equally split up into 3 parts. Why equally split up? Hear me again. The current sees identical paths in traveling to B. All right. If you travel along this, see this. Resistor number 1, number 2, number 3, you are at B. If you travel along this, number 1, number 2, number 3, you are at B. If you travel along this, number 1, number 2, number 3. Number 1, number 2, number 3. Number 1, number 2, number 3. Whichever path you choose, after the third resistor, you are at B. Correct. You choose any path. You imagine yourself to be walking along any resistor, any path. All right. 3 resistors down, you are at B. Correct. What happened, Erlene? This one, you are at B, right? This one, you are at B. This one, you are at B. Tell me another one. This one, you are at B. This one, you are at B, right? Whichever, all paths are symmetrical, right? All paths are identical, right? So current is equally split up into 3 parts. Okay. Now let us follow one current. Just follow one current. Tell me what's happening now. When you reach here, this 2I reaches here. One part is going up, another part is going to the right. I and I. It splits up into I and I, isn't it? 2I breaks into I and I. Now, what about the other 2I? Look at this 2I. That's going over here. That's also breaking into I and I, isn't it? Right. Now, look at the third 2I. This 2I is going up here, and that also breaks into I and I. Okay. Now, let's see what happens afterwards. Tell me about this now. You tell me. Look at this. This I is going up here. I is coming here. Together, that would be 2Y. Okay. This I goes up here. This I comes to the right, 2Y. Okay. Similar way, this I comes here. This I comes here. Together, that would be 2Y. Isn't it? Similar way, this side goes up, this side goes down, goes to the right. This current is also 2I. Now, what actually reaches B now? This 2I coming from here, this 2I coming from here, this 2I coming from here. So altogether it is 6I. Our current distribution is perfect, right? 6I went into the circuit, 6I came out of the circuit. All of you understood this? Okay. Now let us take the simplest path for Kirchhoff's law, simplest path. Okay, what is the simplest path? You can choose any number of loops here, no? I can form so many loops inside this, but you choose the least difficult path. This is the least difficult path. Okay, I can even name it, but it will be complicated, right? If I name it. Okay, I'm just naming it. Okay, I'm using another color here. Just look at, watch out for this green color. Okay, I'm going to call it A, P, Q, B, A. See the loop A, P, Q, B, A. A, P, Q, B, A. Do you see that loop? A to P, P to Q, Q to B, B to back to A. Okay. And as you walk, write down the equations. As you walk, write down the equations. Tell me, what is the first one? A to P. It is current into resistance, 2I into R. It's negative, right? Correct. Because current flows to the right, you walk to the right. So you're walking along the current, isn't it? Isn't it? Now what? This way, current into resistance. What is it? I into R. That's also negative. You know why? Because you're walking along the current, right? Correct. Then you go up. Current into resistance. What is it? 2I into R. That's also negative because you're going up. Current is also going up, right? Then you come back here, you see the negative of cell. Negative of cell means plus E should be equal to 0. So what do we get for this? E is equal to, let's take all these to the right hand side. 2IR, 2IR, IR. 2 plus 2, 4, 4 plus 1, 5. 5 times IR. Equation number 1. And if you were to replace the whole set of resistors with a single resistor, what would it become? It's called R effective, right? You're going to replace the whole set of resistors with a single resistor. So in that case, you can write E as current into resistance. So that is current is 6I, no? The current that went into the circuit is 6I, right? Look at this. This is what I'm talking about. The whole thing will be replaced and you will be putting an extra resistance like this. Sorry, the replacement resistance like this. Understood? So 6I into R effective, right? So look at this. This is what it is. 6I into R effective. This is question number 2. Now equate them, comparing 1 and 2. Comparing equations 1 and 2. What do we get? 6I into R effective is equal to 5 times IR. I and IR cut. So you get what? R effective is equal to 5 by 6 times R.